Solving for unknown coordinates. Now, if you look back at our previous lessons, you'll remember that we learned how to calculate the area of a triangle quite easily, provided that we already knew the coordinates for all three vertices. It was a straightforward process of plugging numbers into a formula. However, in many real-world mathematical problems, and you'll certainly see this in your upcoming exams, the situation is a bit more challenging. Often, you aren't given all the information up front. Instead, you might be provided with the total area of the triangle and the full coordinates for only two of the vertices. This leaves us with a missing piece of the puzzle. One coordinate of that third vertex is unknown, and we usually represent this missing value with a variable, such as k. So, the focus of this specific subsection is to teach you how to use the determinant formula to work backward. Instead of starting with coordinates to find the area, we will start with the area to find the value of that unknown coordinate. In the next slide, I will show you the conceptual approach and the specific algebraic setup we'll use to achieve this. Welcome, everyone. Let's begin our new session on solving for unknown coordinates. The conceptual approach. First, think of the area formula not just as a way to find a result, but as an algebraic equation. Since we are looking for an unknown variable, like the k we mentioned in the previous slide, we are essentially solving for x in a standard equation. Now, here is a very important nuance to keep in mind. While the area of a triangle is always a positive physical quantity, you can't have a negative area in the real world. The determinant itself can actually result in a positive or a negative value. This happens depending on the order in which we list our vertices. Because of this, when you are setting up your equation, you must account for both possibilities. We need to check both the positive and the negative cases to ensure we find all potential values for our unknown variable. Let's look at the general formula we'll be working with. The area equals 1/2 of the absolute value of a 3×3 determinant, where the first column contains our x-coordinates, the second column contains our y-coordinates, and the third column is filled with ones. To make our lives easier when solving, we can rewrite this formula for solving purposes. If we multiply both sides by 2 to get rid of that fraction, we get a much more practical version. The determinant is equal to plus or minus the quantity of 2 times the area. This version is what we will use in our step-by-step procedure in the next slide to set up our equations. Now that we've established that we are moving from calculating area to finding missing pieces of information, let's look at the conceptual approach we'll use to bridge that gap. Step-by-step procedure. Step 1. Identify the given information. Before you start any calculations, carefully list out the coordinates for all three vertices and note the total area provided in the problem. Most importantly, pinpoint exactly which coordinate is missing. This is your unknown variable, which we might represent with a letter like k. Step 2. Set up the determinant. Once you have your values, arrange them into the 3×3 determinant format. You'll place your x-coordinates, y-coordinates, and a column of ones into the matrix structure, just as we saw in the previous slide. Step 3. Expand the determinant. Now, we need to turn that matrix into something we can actually solve. Use the expansion method, typically expanding along the first row, to break the determinant down. This will transform the matrix into a linear algebraic expression that contains your unknown variable. Step 4. Establish the equation. This is a crucial step where many students stumble. Take your expanded expression and set it equal to both the positive and the negative of 2 times the area. Remember, as we discussed earlier, we are using plus or minus 2 times the area to account for both possible locations of the vertex. Finally, step 5. Solve for the variable. You will now have 2 separate linear equations to solve. Solve them individually to find your 2 possible values for the unknown coordinate. Now that we understand the concept of working backward using the determinant, let's break down the actual process into a clear, step-by-step procedure that you can follow every time. In the next slide, we are going to walk through a concrete example together to see this exact procedure in action. Illustrative example. Now, let's put all the theory we have just discussed into practice with an illustrative example. Imagine a land surveyor is mapping out a triangular plot of land. He has already identified 2 corners of the plot at the coordinates 2, 1, and -3, -2. However, the third corner is currently unknown, located at k, -1. If the surveyor knows that the total area of this plot must be exactly 5 square units, our task is to find the possible values for that unknown coordinate, k. Let's follow our step-by-step procedure. Step 1. Identify the given information. We list our 3 vertices as k, -1, 2, 1, and -3, -2. We also note that our area is 5 square units. Step 2. Set up the determinant equation. Using the formula from the previous slide, we place these coordinates into our 3x3 determinant. We set 1/2 of this determinant equal to plus or minus 5. To simplify our calculations and avoid the common mistake of forgetting the 1/2 factor, let's multiply both sides of the equation by 2. This leaves us with the determinant of our matrix equal to plus or minus 10. Step 3. Expand the determinant. We will expand along the first row. Please pay close attention to the signs here, as arithmetic errors are in common pitfall. We take k, multiplied by the determinant of the 2x2 matrix containing 1, 1, -2, and 1. Then we subtract -1, multiplied by the determinant of 2, 1, -3, and 1. Finally, we add 1, multiplied by the determinant of 2, -2, and -3, 1. When we calculate the values inside the parentheses, we get k times the quantity 1 plus 2, plus 1 times the quantity 2 plus 3, plus 1 times the quantity -4 plus 3. This simplifies to k times 3 plus 5 minus 1. After combining the constants, we are left with a simple linear expression, 3k plus 4. Step 4. Solve for k using both the positive and negative cases. As we discussed in the conceptual approach, we must account for both possibilities to find all potential locations for the vertex. In case 1, we set our expression equal to the positive value, 3k plus 4 equals 10. Subtracting 4 from both sides, we get 3k equals 6, which results in k equals 2. In case 2, we set the expression equal to the negative value, 3k plus 4 equals -10. Subtracting 4 from both sides gives us 3k equals -14. Therefore, k equals -14 thirds. To conclude, our final answer is that the possible values for the coordinate k are 2 or -14 thirds. Common mistakes to avoid. First, let's talk about ignoring the plus or minus sign. This is perhaps the most frequent mistake I see. Many students simply set the determinant equal to the positive area. However, remember what we discussed in slide 2. Because the determinant represents a signed area, there are actually 2 different locations in the coordinate plane that can form a triangle with the same area, one on either side of the baseline. If you only solve for the positive case, you are essentially missing half of your answer. Always ensure you solve for both the positive and negative possibilities. Next, watch out for arithmetic errors during the expansion phase. As you saw in our step-by-step example, expanding a 3x3 determinant involves several layers of multiplication and subtraction. A single slip with a negative sign, for instance, forgetting that subtracting a -1 becomes adding 1, will derail your entire calculation. I highly recommend double-checking your signs every time you expand a row. Finally, do not forget the 1/2 factor. It is very tempting to set your expanded expression equal directly to the area provided in the problem. But remember, the area is only half of the absolute value of the determinant. To make your life easier and avoid mistakes, I suggest you multiply the area by 2 right at the start of your equation, just as we did in the example, to get the value of 2 times the area. Now that we have worked through our example, I want to pause and discuss some common pitfalls. Even if you understand the method, it is very easy to lose marks on these specific errors, so please pay close attention. If you can avoid these 3 traps, you will be well on your way to mastering this topic. Let's move on to our final summary of the key takeaways. Key takeaways. First, remember the core formula we've been working with. When you are looking for that missing coordinate, don't just set the determinant equal to the area. Instead, use the relationship where the determinant equals plus or minus 2 times the area. This is the most important step to ensure you don't miss any potential solutions. Second, keep in mind the algebraic process. You aren't just working with a matrix. You are transforming that 3x3 determinant into a linear equation by expanding it. Once you've expanded it, you'll be left with a standard algebraic expression that you can solve using the methods we've practiced. Third, always expect 2 possible answers. As we saw in our example with the land surveyor, there are typically 2 different values for the unknown coordinate. This is because the third vertex could be located on either side of the line formed by the other 2 points, yet still create a triangle with the exact same area. Finally, a word of caution. Precision is everything. Most errors in this topic don't come from a lack of understanding the concept, but from small mistakes in sign management during the expansion process. Be incredibly careful when you encounter double negatives, as a single misplaced sign will lead you to the wrong result. To wrap everything up, let's review the key takeaways from today's lesson so you can approach these problems with confidence. Master these steps, and you'll be able to solve any problem involving unknown coordinates. Great job today!